So far, we've been dealing primarily in linear motion. Linear motion works in terms of displacement, usually in meters, velocity, and acceleration. But when you put a moving object on a curve, things change. Things begin working in terms of angular displacement in radians, angular velocity, and angular acceleration. Radians is a measure of displacement around a circle. 1 radian equals the length of the radius, and the angle measure can be calculated using a formula.
So 360 degrees equals 2 pi radians. So 360 divided by 2 pi, or 180 divided by pi, degrees per radian, that's the conversion factor we can use to go from radians to degrees. And if we take the reciprocal, we'll get the conversion factor that will enable us to go from degrees to radians.
With that being established, angular concepts can be discussed. With linear velocity, v equals distance over time. Now we have angular velocity, omega, in theta over time, and the units are radians over seconds. Similarly, where acceleration is usually velocity over time, we now have angular acceleration, or alpha, which is omega over time, in radians per second squared. Both of these measurements are considered the average speed and acceleration, whereas the instantaneous velocity and acceleration is at the limit as delta t approaches 0. It's important to note that two objects on the same disk might have the same angular speed but completely different linear velocities. If two objects are placed at different points on the radius of a disk and spun around at the same angular speed, the object furthest from the center will have the highest linear velocity because it travels a further distance in the same amount of time. This is what makes angular variables so useful in describing rotational motion. All objects spinning on the disk will have the same angular velocity even though their linear velocities are different. We see this in the equation for tangential velocity. The tangential velocity equals the angular velocity times the radius. As the radius increases, so does the tangential velocity. The same applies for acceleration. These variables, theta, omega, and alpha, can be put into any of the previous equations we have used. From this, we move on to centripetal acceleration, the acceleration around a turn. Even when the speed of an object is constant, the centripetal acceleration isn't. This is because the direction of the object's velocity is constantly changing as it moves in a circular path. When the speed is constant, the vector is always pointing towards the center of the circle, and this acceleration is known as centripetal acceleration and is found by dividing the velocity squared by the radius. Once the equation for tangential speed is factored in, the equation can be written as the radius times omega squared. In order for there to be centripetal acceleration, there must be a force acting on the object. For a ball on a string, the force is tension. For a car on a track, it's friction. And for a satellite in orbit, it's gravity. The term centripetal force is not a new force of nature, like friction or gravity. It simply implies that the force on the object is acting towards the center of circular motion. Take a ball on a string, for instance. The object is kept in circular motion by the string it is attached to. This is the force of tension. In order to find the centripetal force, instead of using the equation for force equals mass times acceleration, we would use centripetal force equals mass times centripetal acceleration. If the force acting on the object, keeping it in circular motion, were to vanish, the object would start traveling in a straight line. Once friction comes into play, the equation is similar to the past one. It would be centripetal force equals mu times the normal force, because the force of friction is what keeps the object in centripetal motion. Gravity also comes into play when things are in the air, like on a Ferris wheel. At the top of the wheel, the centripetal force must equal the normal force, leaving the equation for velocity as the square root of gravity times the radius. It is important to understand that at the top of the loop, the acceleration is subtracted from gravity when doing problems, while at the bottom it is added. So at the bottom, the normal force of a person sitting in the carriage would be greater than at the top. At this point, physicists, specifically Isaac Newton, began wondering about the planets and their movements because they too rotate in a circular motion. He knew that there had to be a force that kept the moon in a circular orbit around the Earth and the Earth around the sun.
But the strength of this attraction depends on the object's masses and the distance between them. The more massive an object, the greater the gravitational force it exerts on another, and the force decreases rapidly the farther apart the two objects are. Isaac described it this way: the force of gravitation is proportional to the product of the object's masses and inversely proportional to the square of the distance between them.
The force of gravity weakens with the square of the distance. Double your distance from an object, and the force of gravity drops by 2 times 2 equals 4 times. Go 10 times farther away, and the force drops by 10 times 10 equals 100 times.
Cap G, the universal constant of gravitation, is valued at 6.67 e to the negative 11, and it was discovered by Cavendish. The formula can be used to find masses of certain objects as well as the distance between them. Just as the force of friction is set to equal the centripetal force, the force of gravity also equals the centripetal force of the planets, and this is how the variables are solved for. It is important to note that the orbital radius is not the same as the normal radius. The orbital radius is the distance between the two center of masses. If a problem is concerning two planets orbiting a point, well, the radius in the centripetal acceleration equation would be the difference from one planet to the central point, or the radius of the circular paths the planets take. Johannes Kepler was Tycho Brahe's assistant in the 1600s. He spent 16 years trying to decipher a model for the motion of the planets.
Tycho had his own system to propose, which combined aspects of both. He put the Earth at the center with the Sun and Moon orbiting it, but let the other planets orbit the Sun.
He found that Brahe's data on the motion of Mars and the Sun held the answer. He showed that the orbits around the Sun were not circular but in fact elliptical.
The length of the string never changed, meaning that the sum of the distances between each endpoint or focus and any point on the ellipse is constant.
This was his first law of planetary motion.
Later on, he expanded this first law to include all of the planets and demonstrated that this shape fit the available observations.
His second law is that lines drawn from the Sun to a planet will sweep out equal areas with equal time distances.
We'll say that if delta T2 is the same time as delta T1, then those areas that the planet has swept out, that's the cool language about windshield wipers, right? Then that area that the planet has swept out is equal to the area it swept out over here.
His third law is that the squares of the periods is proportional to the cubes of the radiuses. To use this equation, proportions are necessary. Rotational motion covers everything from a ball on a string to a runner on a track to planets in space. The use of angular components is what allows us to assess certain problems without running into issues of conversion. Rotational movement is a big part of our everyday lives, whether or not we realize it.